Hi, everybody. Now, in this video, we're doing 3.4, which is the chain rule. Okay, gang. So now we're a chain gang. I thought that was hilarious. That's just me. I find my jokes very funny. I don't know if anybody else does. I don't think so. Anyway, a chain rule has to do with something called composite functions. And a composite function is when you have a function like within another function. So here's m of x, right? So it's x squared plus 4 to the third power. Well, taking x squared plus 4 is one function. Raising the answer to the third power, that's another function. So I could really split this up. If f of u, well, get careful how you say that. If f of u is u to the third power, and g of x is x squared plus 4, so what I'm really doing is I'm taking f of g of x, because the g, I'm calling the inner function, raises x to the x squared plus 4th power. Then the f takes that answer, whatever the answer is, and raises that to the third power. And that's my new function m. So and that's a composite function. It's when you have a function of another function. Basically, it's when you have an inner function, and then you take the answer for that inner function and then operate the outer function on it. And that's kind of this whole map here is kind of showing you that. In other words, I take that's my first function is the inner function, then the second function takes it to the end. Whereas the composite function, I just do the whole thing in one shot. Either way, let's look at some examples of composite functions. Actually, I don't need examples of composite functions. Let's get some calculus here. So these are composite functions because negative 3x is a function and raising e to a power is a function. Raising e to a power is a function and multiplying something by negative 3 is also a function. That's what happens when I take these two functions. Notice that if I do, the order makes a difference. See here, f is e to the u and g is negative 3x. Well, if I do the g first followed by the f, I get one answer. If I do the f first followed by the g, I get a different answer. So you see that it doesn't necessarily mix and match. Doesn't necessarily mix and match. Anyway, let's get to some actual calculus here. Okay, I want some calculus now. That's what I want. I want calculus. Okay, here's the chain rule. So if m is equal to e of I, m is equal to e of I of x, so the derivative is e prime of I of x times I prime of x. Another way of saying this is that it's the outer derivative times the inner derivative. That's a very simple way of saying it. That's why I always say it. Notice here it looks like almost like fractions. dy dx equals dy du over du times du dx. It's almost like the du's cancel. Isn't that kind of cool? Anyway, let's just do some examples. I think this is much easier if we just do examples. Chain rule looks complicated when you see it written out, but when you do the examples, it's actually one of the easiest things we're going to do and funnest. So m of x is equal to 3x squared plus 1 to raise to the 3/2 power. Well, basically, the inner function is going to be the 3x squared plus 1. The outer function is raising to the 3/2 power. So, I prime, so I is the inner function, 3x squared plus 1, and the outer function is u to the 3/2. So basically, I'm taking the derivative of the outer function. So I keep the 3x squared plus 1 intact, and I take the 3/2, stick it out here, and knock that down to 1/2. Then I have to multiply it by the inner function, the derivative of 3x squared plus 1, which is 6x, and that's my final answer. So in totality, it winds up being 9x times 3x squared plus 1 to the 1/2 power. And the function m is composite via view. So here we have, e to the 2x squared, 2x cubed plus 5. So the inner function is the 2x cubed plus 5. The outer function is the e to a power. Well, the derivative of e to a power is just e to the power. And I multiply that times the inner derivative. So the derivative of e to a power is just e to that same power. times the inner derivative, which is 6x squared, because the derivative of 2x to the third is 6x squared, and the derivative of the 5 just disappears. Anyway, my final answer, nice and neat, is 6x squared times 2e to the 2x cubed plus 5. And let's look at this guy here, the ln of this whole sucker here. Well, the inner guy there, that's the inner function, then the ln is the outer function. Now, the derivative of ln is 1 over the function. So the derivative of ln is 1 over whatever was inside, which is x squared minus 4x plus 2, times the derivative of what was inside, which is 2x minus 4. And my final answer is 2x minus 4 over x squared minus 4x plus 2. And let's do a nice example. Now, sometimes you have chain rules, right, where there's more than one function involved. And we have that here. Because the outer function is e to the power. The inner function is 1 plus the ln x squared, and the inner function is just plain ln x. So basically, even though this sounds really complicated, it's going to be very simple. Because the outer function is going to be e to the 1 plus ln x squared, because the derivative of e to the power is just e to that, is just the same e to the power. It doesn't change. Now the inner function is the 1 plus ln x squared. So I'm looking at this like ln x itself is the variable, so it's just going to be 2. The 1 is going to disappear, and it's going to be 2 times ln x, which I have there right there, 2 times ln x. And finally, the derivative, the inner function is the ln, and the derivative of ln is 1 over x. So we have, if I put it all together, I get 2 over x times ln x times e to the 1 plus ln x squared, which is kind of cool and awesome. Chain rule actually makes things very, very easy. Now this is interesting. Now this is just things that happen. You know, if you have a function raised to the nth power, the derivative is going to be n times that function to the n minus 1 power times f prime, because this whole thing here is the outer derivative, the f prime of x is the inner derivative. These are just kind of like, I wouldn't even teach these as rules. They're just kind of like things you observe when you do this. The derivative of ln of some function is going to be 1 over the function times the derivative of that particular function. And the derivative of e to the f of x is going to be e to the f of x times the derivative of f of x. So the f prime of x is the derivative of the inner function, e to the f of x is the outer function. And that's good. So let's find some derivatives here. E to the 2x, ln of x squared plus 9, and 1 plus e to the x squared cubed. So we got to work it out first. Let's start with a. E to the 2x. E to the 2x. Well, that's going to be e to the 2x. That's the outer derivative times the inner derivative, which is just going to be 2. So my final answer is 2 times e to the 2x. Here we have the ln of x squared plus 9. Well, the outer derivative is 1 over x squared plus 9. The inner derivative is the derivative of x squared plus 9 itself, which is really just winds up being 2x. So it's 1 over x squared plus 9 times 2x, or I could just write it into one fraction, 2x over x squared plus 9. And finally, the last one, which is the most fun, is my outer derivative is raising to the third power. So I take 3 times this whole parenthesis to the second power. Then I take the derivative of the parenthesis. Now this is actually going to wind up being a second chain rule here, because the derivative of this sucker, well, the derivative of 1, that just disappears. The derivative of e to the x squared is e to the x squared, but times the derivative of the inner function, which is the x squared. So I have 3. So in totality, I just have to. So the derivative of that inner function is 2x. So putting it all together, I wind up having 6x times e to the x squared times 1 plus e to the x squared. That whole parenthesis squared. Try to say that in one breath. And that is the chain rule. Chain rule is very awesome. And maybe I'll do, let's do a couple of, I want to do a couple of homework problems too, because there's a lot of, chain rule is, like I say, when you do the examples, it's just easier. So let's it's not channel yet. Let's place. Well, I'm trying to find. Let's get one that's all right. Find f prime of x. Well, it's going to be 13. Like I'm saying, it's going to be 13 times 1 minus 9x raised to the 12th power. And this is the outer derivative. And then times, now normally I wouldn't have to put that multiplication dot, but I want you to realize that I want to have inner outer times the inner derivative, which is -9. And there you go. Now, normally I would not necessarily write it this way. I would write just negative, what's 9 times 13, 120, 117, whatever, it doesn't matter. This is it. That's my outer, that's my inner, we're all good. Okay, let's look at another. I just want to do a couple of examples with you. Okay, this is going to be the same thing. It's going to be 15 times 3 plus 2x raised to the 14th power. Oops. Raised to the 14th power, and times the inner derivative, which is going to be 6x squared. And it oh, I left something out. Sorry about that. That was just a typo. I left out the exponent here. Whoops. There you go. I just copied it wrong. Whatever. Anyway, let's try now. I just want to do a couple examples here. Just get to the same. This is kind of the same thing. Okay, this is going to be, well, the outer derivative is e to the 4x. And we multiply that times the inner derivative, which is just 4. Because the inner function is 4x, and it's just 4. And this one here is going to be, well, first it's just going to be 5 times e to the -2x. And multiply that times just -2. Because that's the inner derivative. And even though this is a very dorky way to write it, but this is correct. I personally, I'd write -10 times e to the -2x, but it doesn't matter, it's correct. Okay, now the inner function is that little polynomial. The outer function is the square root. Now, for a square root, that square root is really x squared plus 9 to the 1/2 power. So I'm gonna notice, and let me just emphasize that. Oops, let me just. So this is going to be 4. Let me rewrite this here for you guys. This is going to be 4 times x squared, 8x squared plus 9. So really, see, I could write a square root as 8x squared plus 9 to the 1/2 power. So the derivative is going to be, I'm going to do some surgery now here. Well, actually, no, let me just copy. So the derivative here is going to be 4 times 1/2 times this sucker to the 1/2 minus 1, which is -1/2 power. And so let me just get rid of all this other guy. But I have to multiply that now. I have to multiply this whole thing by the inner derivative. And the inner derivative is 16x. And there you go. And that's it. And that's the answer. Again, I personally would like to clean this up and make it look nicer, but I just want you to see the calculus now. This is not an algebra class, it's a calculus class. So I'm assuming you actually know some algebra. maybe that's not a good assumption, but that's what I'm thinking. Let's find a triple decker one. I want to look for one that's a triple decker. Well, if anyone ever, I just want to mention here that if anyone ever, well, this one here, let's just this one. It's gonna be 5 times. Now we saw that we saw kind of a rule that I'm going to do the derivative of the inner guy times over the inner guy. So it's going to be 6x. And on bottom, I'm going to have 1 plus 3x squared. This is kind of follows a rule that we had seen already. So let's, this is a little different because this is going to be, it's not the ln of x to the 5th power, it's the ln of x and raised to the 5th power. So this is going to be, this is an interesting function. This is going to be 5 times the inner function, which is 8 plus 9x, 8 plus ln x, raised to the 4th power, times the derivative of the inner function, which is actually just 1 over x. Because the derivative of 8 is just 0. The derivative of ln x is 1 over x. And that's going to be the answer there. There you go. Nice work. If I must say so myself. And no, I want to find one where it's let's see, line. I'm trying to find one where it's, these are all straight chain rules. I want to find one where it's a triple. Oh, this is going to be fun. This one here is going to be a combination of product rule and chain rule. In other words, 5x times e to the 7x, that's a product. So I'm going to do the product rule, but within the product rule, I'm going to need the chain rule to get the derivative of e to the 7x. So this is a nice one because it kind of combines 2 different rules. So we're going to do 5, that's the first derivative, times e to the 7x, and then plus 5x times e to the 7x times the inner derivative, which is 7x. The inner derivative is just 7. So I'm going to write times 7. There you go. It's very awkward and cumbersome when I write it this way. Personally, I like to, as I said, I like to write these better, nicer, and neater, but this is technically correct. Alrighty. Let's see. Okay, this one is, what a pain. This is going to be quotient rule. This is going to be quotient rule. Where did 7 come from? It's going to be 7. Oh, wow, what a pain this is going to be. Okay. Let's just take a quick look here. Simplify. Oh, okay. So it's 7x over. Wow, this is a real pain, this one. 7x. That's just 7. Now I'm intrigued by this one. So this one I'm gonna have to work out on pencil and paper. Then I'll give you the answer. Okay, well the answer is choice D, and I'm going to show you how I got that. I actually put the steps over here. So this is on your Google Docs. So you could always look at this. So the derivative of ln of, because it's really not so much chain rules, more quotient rule. So I want the derivative. So I want the bottom times the derivative of the top minus the derivative of the bottom times the top over the bottom squared. X to the 3rd squared is x to the 6th. And now I'm going to cancel out x squared from everywhere. And I have this guy here. I'm gonna multiply top and bottom by 7 plus x. And I get this guy here, which is that is choice D. This is choice D right there. And those are the steps how I got that. All right. Well, this has been loads of fun. Hope you enjoyed it as much as I have. It's been thrilling and exciting and That's math. That's the beauty of math. Anyway, that was Chain Rule. Now you're all part of the Chain Gang. I said that joke already. Okay, next time. Bye.